Okay, so can you hear me?
Yes.
Okay, great. So let's get started. So I will share the screen. Yeah, so first, a couple of announcements. So the first one, there are no office hours tomorrow. So usually I have office hours from 2:45 to 3:30, but I have to host our job candidate tomorrow. So we have no office hours. So if you have any questions, just contact me by email. We can set up a time at another time on Friday or weekend. And has any of you attended to today's job talk? No? Anyone? No. Sorry. Maybe I should have let you know beforehand. But our job candidate is visiting campus today and tomorrow, and his name is Yang Wan. So Dr. Yang Wan is available tomorrow for lunch and also office hours. So usually the faculty attends lunch, but I don't see any other faculty members to attend tomorrow. So if you are interested in, you can join for the free lunch, but just let me know beforehand. Is anyone interested in? And even you don't join the lunch, it's really welcome to visit his office, the 1185 FAB, just next to my office, for chatting about data science and machine learning. So his research area is machine learning, and so we don't have any expert in machine learning in our department, so it's a good opportunity to talk, and also it can give him a good impression of the department. Okay, so today's topic that we just to finish the chapter 1. Chapter 1 we have almost finished. Just the overview of the textbook has not been finished. So chapter 1 just finishing. And we study chapter 2 today. So just basic concept of regression and data analysis, data analytics, basic regression concepts, and also the performance measure of the statistical model, regression models that we study the mean square error. Probably we have studied mean square error in other classes such as Stat 5030 or even 5800 or 6840, but we study the training MSE and test MSE. So training error and test error. And also that we study the bias variance trade-off. So basically, when we construct a regression model, that we can decompose the error into basically 3 components, and one is the bias, and the other is variance, and the second one is variance, and the last one is the so-called irreducible error. So it's the intrinsic error. So we discuss these. Okay. Do you have any questions from the last lecture or quizzes? The quizzes allow 2 attempts usually, but if the quiz is a multiple choice question with a few choices, like 3 or 4 choices, sometimes you only have 1 attempt. But the numerical questions, always you have 2 attempts. Okay, so this is an overview of the textbook. So chapter 2 is just overview of statistical learning and also general theory for statistical learning, general ideas of statistical learning. And chapter 3, linear regression, this is almost a review of 5030. Chapter 4, classification, the one is logistic regression. Maybe it has been covered 50-30. How many of you have taken 50-30 last semester? Do they cover logistic regression or not? No. Okay, so then we will cover in detail. Basically, logistic regression is a regression model with binary response variable. So the outcome is, for example, benign or malignant, or unsuccessful or successful, or no or yes. So the binary regression. So that is totally different from linear regression. In linear regression, the response is continuous. For example, the price or the height of people, or yeah, something like that. So continuous temperature. So those variables are response. And if response is continuous, we assume some normal distribution in error or something. But the response is binary. It's totally different. So it's totally different thing. And also we study other classification models. So these are not covered in other courses. So linear discriminant analysis, quadratic discriminant analysis, and nearest neighborhood, k-nearest neighborhood. So maybe the some of these are briefly covered in Stat 6840, but other than that, we haven't covered. So LDA, QDA, and KNN. So these models can deal with the categorical response. So logistic regression is almost specific for binary, but the LDA, QDA, KNN can be applied when response is category, such as blood type, A, B, O, and AB, or maybe what some species of animals, the tiger or lion, or what, the bears. Yeah. And chapter 5, the resampling methods. So we study cross-validation and the bootstrapping and so on. So resampling means that we have only one sample, but we sample from that sample. Suppose we have 100 observations of the data, and suppose the sample mean of the variable x is 100. But we don't really know how reliable that number 100 is. So we resample from those 100 observations. For example, we randomly take our observation maybe 50 times with replacement. Then we can calculate the sample mean again. That sample mean may be 105 or 98. And if we repeat that kind of procedures, then we can evaluate how reliable our sample mean is. So sample mean of 100 observations maybe just one number. It's just one number, for example, 100. But the resampled sample mean has some variability, such as 98 or 105, and based on that variability, we can evaluate the reliability of the sample mean of all observations. So we studied some methods to use this resampling method for evaluating models. Chapter 6, linear model selection and regularization. Model selection has been covered in 50-30, I guess. The students in the 50-30 last semester, I think the course covered model selection, AIC, yes. Okay, so that is covered, but also we discuss regularization. So regularization is a little bit different idea. So the model selection is more, the digital, the choice of predictors. Suppose we have the candidate of predictors x1, x2, x3, x4. Then, okay, so we decide which variables are useful, maybe x1 and x4. Then we regress y on maybe constant plus constant times x1 plus the constant times x4, maybe plus error. So this is the model selection. But the regularization does not restrict predictors. So we always think about the full model, maybe beta naught plus beta 1x1 plus beta 2x2, beta 3x3, and beta 4x4. But since we have so many variables, we restrict some, we put some restrictions on these coefficients. For example, the sum of squared coefficients should be small, or we penalize the sum of squared coefficients so that the coefficients do not become large. Probably you have studied the collinearity in the linear model. For example, x1 and x2 are similar variable. If x1 and x2 are similar variables, beta 1 and beta 2 are difficult to estimate. For example, if x1 and x2 are almost the same, then b1 is equal to 1 and b2 is equal to 1, or b1 is equal to 2 and b2 is equal to 0, or b1 is equal to 0 and b2 is equal to 2. So these three cases are hard to distinguish, right? But if we penalize the size of errors, size of coefficients, then we can uniquely determine this. For example, suppose that we penalize b1 square plus b2 square, then the 2, 0 or 0, 2 are inferior to 1, 1. So in that way, that we can decide the coefficients more reasonably. Yeah. So that is the thing we have to study. And yeah. And chapter 7, the moving beyond linearity. So usually we start with the regression by linear relationship between x and y. And why? Because it's the simplest possible relationship between x and y. But that isn't always true. Okay, so maybe for this data, maybe the linear, straight line makes some sense, but if we use maybe quadratic curve, then it may become better. So that is called polynomial regression, but also that we think about other ideas such as the splines or local regression. So local regression means that we fit the curve locally. Okay. So the splines means that we connect several curves with some smoothness. And the GAMS is so suppose the y's are explained by x1 and x2, but we use the polynomial of x1 and the polynomial of x2. So we don't consider the x1 times x2, but we have more flexibility between the relationship between y and each predictor. Chapter 8, the tree-based methods. So basically, we separate cases in regression analysis. So suppose that we have the space x1 and x2. So x1 and x2 are both predictors, and for each observation, we observe y value. But maybe it's good to separate this into three cases. So here and here and here. So this is called tree based method, because if we make a diagram, then that becomes the 1, 2, and 3 or something like that. So this is called tree. And support vector machines. Support vector machines is a little more advanced method than regression analysis. So I will explain later, but usually that we consider relationship between x and y only. Sorry, I don't have enough space to write, so maybe yeah. So usually we only consider x and y, right? So maybe I would say that we have x, maybe x1, x2, x3, 3-dimension, and we explain y. But the support vector machine, okay, so suppose x is in R3 here, right? And y is suppose in R. Then we create an intermediate space, maybe R10 or something. Then So this is the fixed map. Then we consider estimating the this function f. So we at first expand the space. We map these predictor values to higher dimensional space. Then we explain why. Then we can better explain some situation. Yeah, we discuss in detail later. And chapter 10, deep learning. So deep learning is a neural network. The neural network is basically the multiple logistic regression. Yeah. So if you haven't studied logistic regression, then we have to study logistic regression first. Chapter 10, maybe we briefly cover the chapter. And chapter 3 to 10 are all supervised learning. And chapter 12 is unsupervised learning. So principal component analysis, that is, for example, making a business cycle indicator out of the 10 different components. And k-mean clustering. Yeah, so that is the clustering problem. So that it's similar to classification problem, but the labels are not given. So those are the things. Okay. Yeah, and so that's it. So do you have any questions for the materials? Maybe one natural question is, what is chapter 11? But I don't really know. I think chapter 11 is something different. I think, yeah, but I'm not really interested in covering the chapter. I think, yeah, you can check the textbook, but we don't cover chapter 11. Maybe more chapters, but we don't cover.
Survival analysis and censoring.
Oh, survival analysis and the censoring. Yeah, yeah, that's true. So that is, some response is censored. For example, the response variable is the lifetime, but some people have not died, so just it's censored at some point. Yeah, we don't cover that. Yeah, so do you have any questions? And each chapter have the lab session, so that explains how to implement these models in our language. So we also cover those. Yeah, and next one, the how to use R. Have you installed R and R Studio into your computer? Okay, so does anyone have any trouble? Then you can ask. There are 10 people here, so if you have trouble, then you can ask the question to whom to the students in a similar environment. All of you have been successful to install the softwares? It's fine. Okay, great. And R Studio, there you can install. So today's quiz uses R, just a very basic question. Yes. Okay, so that's chapter 1. Okay, so do you have any questions? Yeah,
I've got a quick question. Is there any particular reason why we focus more on R as opposed to something like Python?
No. Just to use in a class, R is easier to install, so that is just one reason. And yeah, you can use Python for machine learning. That's true. Yeah. I don't have, and I'm a statistician, and statisticians use R, and the computer scientists use Python. So that is the general tendency. Yeah. And the R has more, statistical procedures. And Python has more, machine learning procedures. Okay. Yeah, for example, the stepwise AIC procedure isn't in Python, at least in popular packages. Okay. And chapter 2, we start. The slides are already available in Canvas, the statistical learning. So yeah, probably you are already familiar with the regression analysis, but in regression analysis, the objective is to predict Y. And in this first example, the Y is sales, and the predictors X are advertisement budgets for TV and radio and newspaper. And this data is available for 200 markets. So sample unit is a market, and then we have 200 observations. So basically, based on this data, that we want to decide which advertisement budget should we increase, TV, radio, or newspaper. So data science is focusing on implication in the business or the specific domain. So the always question is like this. So we need some implication based on the regression analysis. So this is the basically the marginal distribution of sales against each of the predictors. And we have sales on the y-axis. And for x-axis, we have TV and radio and a newspaper. And TV advertisement budget and sales have a very clear relationship, positive relationship. And the radio also the clear, kind of clear relationship, slightly vaguer than the TV. Newspaper, it's not really clear. Yeah, so for each of the predictors, for example, we can fit the simple regression model, simple linear regression model. But of course, it's also possible to use all of these predictors, maybe X1 TV, X2 radio, and X3 newspaper. And also maybe we have some interaction between these terms. For example, if people see ads on 2 different medias, then people are more likely to buy the product. Or maybe the other way around. So if people see advertisement somewhere, then it does not matter whether it appears in other places. So in linear regression, we often start with this model. So we regress Y on X1 and X2 and X3, as well as intercept. And epsilon is an error term. And usually the beta 1, beta 2, beta 3 are unknown. So we have to estimate these numbers. And estimates are denoted by beta I hat. So it's not true beta I, but it's something close to beta I. But in general, we can have relationship like this. So Y is a function of X1, X2, X3, and error. So in general, we want to estimate this function f hat. So in conventional classical statistics, X is assumed to be deterministic, so that we don't have randomness in X. So sometimes the X has some randomness, maybe some measurement error, or we have to specifically consider range of X. X is uniformly distributed from 0 to 100 or something. Yeah, but in this regression analysis, I think that almost all the models in this textbook, X is deterministic, so we don't consider the randomness in X. So epsilon is an error, so random variable. So epsilon is random, so and f of x1, x2, x3 is deterministic, so y is random again. So basically our objective is estimating this f function f. So this f. So it can be used for forecasting. So given advertisement budgets on TV, radio, and newspaper, we can predict the sales. And also, sometimes we are interested in the inference. For example, that we want to see the value of beta I. So when we spend 1,000 additional dollars on TV, how much sales that we can expect, how much more sales that we can expect. And also sometimes we are interested in whether or not the beta I is equal to 0. So suppose you have abundant budget for advertisement, but you are wondering if newspaper advertisement is useful to increase the the sales. Maybe if the media has a very bad reputation, maybe the advertisement may decrease the the sales. Right? So when I see I surf the internet, then some annoying ads appears, then I decide not to buy that product. So that is also possible. So the question is whether beta I is equal to positive, significantly positive, or not really significant, or maybe significantly negative. So that kind of question that we want to answer sometimes. Yeah, and do you have any questions so far? Yeah. So just a review of regression idea, but yeah. So at least the 50-30, we don't discuss the formulation such as this. So we are thinking about more general, more complicated models. So a measure of error. So basically, when we make a prediction model, we want to minimize error. But in what sense? So it's not clear, but usually the most popular measure is this mean squared error. So that is the average of square of actual yi response and the predicted response. So this is similar to Euclidean distance because this is the sum of squared distances. So it's most natural measure. And also this is a kind of the average, so mean of the squared error size. So we put 1/n. Yeah, so this is a sample version of the expected size of squared error. So the y minus y hat, we have y1 to yn, but in general, we want to minimize expected the squared error size. So this MSE is the sample version of expected error, this expected the square of y minus y hat. So capital Y, capital letters are used when the quantity is random variable. And the lower case is observed numbers. So usually we see yi as the realization of random variable. Sometimes still we assume yi is random, but that is conceptual difference. But sometimes the capital letters are used to represent matrix. So sometimes it's confusing. Yep. So now that we discuss the reducible and the irreducible errors. So think about the relationship between the weight and height of Americans. Then maybe height can predict weight, right? And maybe height, the weight is three-dimensional quantity. So maybe height cube is a good indicator to explain weight, right? But also the section of the human is not different in size, not much different in size. So 107 centimeter person and 180 centimeter person. So usually they are different in terms of height, but the difference in height, sorry, the difference isn't really large in terms of maybe width or depth. So maybe height square is another indicator or something like that. And if we improve the model, then we can improve the minimize the error. But still, even if for the best specification, we have some errors because the height does not entirely determine the weight. For example, maybe gender difference, maybe, I don't know, but for the same height, maybe males are a little heavier than females, maybe. Yeah, and also some other factors, maybe age or race. I think the age 55 has the most weight given other conditions, and so on. So that means if we only use height and weight, we can only explain the part of the weight by height. So that involves some irreducible errors. So mathematically, it can be formulated in this way. Okay, so we have the x and y. X is predictor and y is response. N is index for the individuals. And suppose n is available from 1 to n. And we want to evaluate the size of error. So we construct the regression model and we estimated f. So we have f hat. Then we say y hat is equal to f hat. Then error size is y minus y hat. So we want to calculate the expected size of error. Okay. Sorry. Yep. So expected size of error. And okay, so y hat is equal to the f hat, and y is equal to fx plus epsilon. So our assumption is y is equal to f of x plus epsilon, and we estimated f. So y minus y hat is f minus epsilon minus f hat. And if we change the order, then that is the so f minus, maybe I should say in a different way. So we can say that this is f minus f hat plus epsilon and square. So we decompose this into 3 terms. So one is the square of f minus f hat, and another is square of epsilon square, square of epsilon, and the other is the cross term, epsilon times f minus f hat. So we have 3 components. So 1, 2, 3. Yep. And now we consider the second term. Okay. And our assumptions are observations are independent each other. So epsilon are independent each other. So that means that the f hat is calculated based on the y1 to yn, and also x1 to xn, but these are not random anyway. And epsilon is general observation. We can say this is just a general new observation. I would say x0, y0. So epsilon only depends on y0. And the y0 and the y1 to yn are all independent. So these are independent. So that means the expectation of epsilon times f minus f hat is equal to expectation of epsilon times expectation of f minus f hat. So generally, I would say that generally maybe u and v are independent. Then expectation of u times v is expectation of u times expectation of v. So you can decompose it. And epsilon is an error. So by definition, the error has expectation of 0. So this is expectation of epsilon times expectation of f minus f hat. So this term actually disappears. So this is actually 0. So we only have the first term and second term. So first term is the expected value of the difference between f and f hat. So this is the error of f hat. So f hat is not good enough. So that is one thing. And the other part is epsilon. And epsilon is, intrinsic error. So the truth is y is equal to f of x plus epsilon. So epsilon always appears. So we cannot reduce this error size. So we can decompose the squared error size into this reducible error and irreducible error. So first term is called reducible error, and the second one is called irreducible error. Yeah, here. And in real world problems, the irreducible errors that exist, but the y is partly determined by the factors not included in x. So if we add more variables, maybe epsilon gets smaller. For example, the sales y in the previous example may also be influenced by temperature or business cycle, rival companies' products, etc. So that if we introduce these predictors, maybe expectation of epsilon square gets smaller. Yeah, so that's the concept of irreducible and reducible error. Yeah, and in reality, the f is not observed. F is truth, but it's not observed. So actually, we cannot really decompose in real examples. So if this is a simulation, if we know the true f, then we generate epsilon. Then we know all the structure. So we can generate those observations, x, y, x and y, x1, y1 to x and yn. Then we can estimate f. Then we can calculate reducible error and the irreducible error. But in real data set, the f is not known, so we cannot really decompose it. So this is conceptual, the decomposition of error size, squared error size. Do you have any questions? Yeah, I think the last time a few of you are not here. I think the Luke and maybe some other anyone who were not here today. Maybe Nicholas not here. Nicholas, were you here today, Nicholas? Not Nicholas, Nathan. Sorry. Yeah, maybe you two can introduce yourself briefly. So last time, students introduced each other. So maybe just briefly, what's your major and what you are interested in, maybe, and of course your name.
Yeah, I'm
ahead.
Luke. I'm an actuarial math major. Yeah, I really like sort of any sport. Yeah.
Oh, you're a tennis player, right?
Yes. Yes.
That's a competitive sport. So you will go to Wimbledon sometime in the future?
Well, maybe just to watch.
Okay. Okay, Nathan, can you introduce yourself?
Hi, I'm Nathan. I'm master's student mathematical statistics, and it's my second semester here. But I don't have any cool interests, unfortunately.
Okay, good. So does anyone want to say, introduce again to each other? Yeah, many of you have taken my courses before. Yeah, okay. So now we continue. Yeah, so the next topic is, how to estimate F. And there are several methods, but overall, we have two different ideas. So one is the parametric methods, and the other is non-parametric methods. So the parametric methods means that the truth is expressed by a few numbers. So that is often true in science. So the number of parameters is finite and fixed. So that means okay, we have 200 observations, but we only have 4 parameters. And if we have 1,000 observations, we can improve the model, but still we only have 4 parameters. So the number of parameters are fixed and small. So that is the parametric methods. And the linear regression, maybe logistic regression, generalized linear model. So those are all parametric methods. And the other way is non-parametric methods. So the model cannot be represented by the finite and fixed number of parameters. So that means usually the number is still finite because data set is finite, but it's not fixed. So example is here. So y hat is defined by the mean y value of 5 nearest observations among x1, y1 to x and yn. So we don't really have the specific number of parameters. So for each new observation, so each new observation x naught, we have to find the 5 nearest in observations. Then we have to take average of y1 to yn. So it's more data oriented and the data driven, and it's not determined by the specific number of parameters. So both methods have some strengths and weakness. So parametric methods, it's simple. So that's one good thing. And maybe computation is faster. And also interpretable. So what is beta 1? Beta 1 is positive. That means the TV advertisement is useful for increasing sales. But the non-parametric methods are more flexible. So yeah, and some disadvantages. Parametric methods are not flexible, and non-parametric methods sometimes needs a lot of observations to estimate. For example, these methods cannot be applied if you have only 5 observations, probably, because that is just, we take the mean always. So if we have 5 observations, maybe fitting a straight line is at least better than just taking average of y values. So you can imagine that non-parametric methods needs more observations. If we have 1 million observations, probably it's good to use the non-parametric methods, but if we have only 5 or 10 observations, probably it's not good. Questions? Yeah. And the next concept, the trade-off between accuracy and interpretability. So this is especially important in business environment. So more or business or even science environment. So more complicated model is often hard to justify by logic. So let x be the diameter of the shell and y be the weight of the shell. And what model is the best? Okay, so we have to go the parametric, suppose. Then maybe you can fit the y is equal to alpha times x cube, maybe plus epsilon if we need. Okay, so usually we have error. And maybe also that you can fit y is equal to alpha times x to the power 2.1. And suppose, okay, so we calculate the MSE. And MSE is equal to, okay, so 0.9 here, and MSE is equal to 0.8 here. Which model you will choose? So diameter is one-dimensional quantity. The weight is three-dimensional quantity. So the first model is pretty, natural model. And the second model, MSE is smaller, but 2.1 is a little bit strange. So if we got this result, which model you will use? Maybe the survey takes time. So, but just raise your hand if you want to choose alpha x cube, the first model. 1, 2, 3. Okay, William also. And how about this next one? Who you want to choose? Raise your hand if you choose the next model. Y is alpha x to the power 2.1. Yeah. So the opinions are divided, right? So the no right answer for this. If you're a more data-oriented person, you will choose the second one. But if you really need more physical meaning, maybe you go the first one. So we don't have a uniform answer for this. And the flexibility of the model and the interpretability. So usually we have trade-off. So the subset selection, suppose we have 100 predictors and we choose the best set of predictors. So this has higher interpretability. So these predictors are useful for prediction. And also, if we only have a few predictors, we can interpret coefficients. And lasso is even higher, maybe, possibly. I would say this direction. So lasso, but it's still similar, but the lasso, the estimates the full model, but in the model algorithm, the more questions becomes 0. So it's similar to subset selection. So maybe similar, sorry, maybe similar. And least square methods, this means the full model. So full model, still we can interpret coefficients, but we have more questions, the more predictors, so it's harder to explain the model, interpret the model. So generalized additive models, so that means instead of y is equal to beta naught plus beta 1 x1 plus beta 2 x2, we have a little more general function, maybe g1 of x1 and a g2 of x2. So it is more flexible, but the less interpretability. And trees is a kind of intuitive for human. So we separate cases. So if blood pressure is more than 150, then the people are in the high risk group for hypertension, so maybe heart stroke. So that we have to go into detail about the what's the BMI of those people or something like that. So it's a more interpretable, but the mathematically speaking, after we divide cases, we fit the linear regression. So it's at least it is less interpretable compared to linear model. And more bugging, boosting. So basically we take the average of the tree-based methods. So we have more smooth estimated function, but the less interpretability. Support vector machine, that we map lower dimensional predictors into higher dimensional space. So the model is more complicated, so less flexible. Probably neural network, even lower interpretability, and even the estimated coefficients are not really identifiable. So just we optimize the error size. So even the lower interpretability, but higher flexibility. So we have trade-off. So it's especially important in business environment. For example, you develop the model for the default risk of people. And suppose that the people's BMI matters for the default risk by neural network. Then you use the body mass index, BMI, to decide the risk of the lending money. That is arguable. So maybe in some specific population that's true, but it's not really interpretable. So that's also one thing to think about it. Yeah, and also even we only have reasonable variables such as income or the years of employment or educational level, then we use those predictors to predict the default risk. But if the model is very complicated and we are not sure what's happening in the model, then probably the management is more reluctant to use the model, maybe compared to linear model. So that is one thing we have to consider. Do you have any questions so far? What time? 7:21. Okay, still we have time. Yeah, so next we go to the some details of supervised learning. Yeah, so we have the supervised learning examples. The one is the regression problem. So that is that we have the quantitative response, typically the real valued variable. And the other is the classification. So this is for qualitative response, the binary, such as the success failure, or multi-class, such as species ABC. And for regression analysis, we can use linear model or something. And in classification problems, sometimes we can use similar methods as linear regression. So one is called logistic regression. So for example, we want to explain the gender by some physical variables, maybe the percentages of water or weight, height, and body fat percentage, and so on. X1 to XP. Okay. Yeah. So here, the interesting. So age itself probably doesn't explain the gender. Maybe if age is 100, maybe they are likely to be female, but very little information. But if they combine, for example, the body water percentage and the age, then probably it's good indicator to predict the gender. And for this kind of the binary response variable, male or female, we can still use a regression model because the two numbers are always ordered, right? Suppose we make female as 0 and male as 1. Then it's ordered. So maybe this is not a good explanation, but we only have two values. So we can calculate the probability of male. So our fitted value may be 0.8 or 0.4. If 0.4, that means we have 40% probability that the person is male. If 0.8, 80% probability that the person is male. So we can say the probability of the female given the predictor X is described by this. And here, the one issue is that if we use just beta naught plus beta 1 x1 plus blah blah plus beta p xp, this part belongs to, this part can be any real number. So it belongs to this set, negative infinity to positive infinity. But that is a problem because the left-hand side is a probability. So it should be between 0 and 1. So if we got 1.1, that isn't the best answer, right? Because suppose male is coded as 1, female is coded as 0. 1.1 always has some error. And if male, error size is 0.1, female, error size is 1.1. That isn't good. If we say the the predicted value is 1, always the error is smaller. So actually the right hand side there should range from 0 to 1. We shouldn't go out of that range. So for that purpose that we have to make a function f. Suppose maybe this inside is eta, then depending on the eta value, then the f of eta should be between 0 and 1. So like this. So sorry. And here is 1. Y is equal to 1. And here is 0. And suppose this is equal to y, and the y is equal to f of eta. So f should be a function that whose range is 0, 1. And usually open interval 0, 1. So we don't consider the probability of 0 or 1. So that cannot be justified if only one exception appears. Yeah, so this is the concept of logistic regression. So now, if the response is binary, still we can use some kind of regression model. So it's different from linear model in the sense that we have function f. F is called link function, and also since we are thinking about probability, we don't have any error term. So probability is expectation. Probability is expectation. If male is 1, female is 0, then probability of male is a kind of expected value of this variable, right? So once we take expectation, then error term disappears. So even the usual linear regression model, y is equal to f of x plus epsilon, if we take expectation on both sides, error is assumed to have the expectation 0. So E of y is equal to f of x. So we don't have error term. Yeah. So this is the concept of logistic regression. We will discuss this in chapter 4 in detail. And okay, so next thing we think about is, okay, we have predictor and the response, right? And we considered the case that y is binary. And later we consider the case that y is categorical, such as ABC. But what happens if x is categorical? Suppose y is just continuous. And in this case, still we can use linear model as usual in this way with dummy variables. So for example, the data is here. Okay, so price of houses and the square footage and age and the style of the houses. So we want to explain price by these 3 variables. Maybe I would say x1, x2, x3. And the price is in continuous scale. Maybe it's not negative, but usually we can assume this is just it ranges from negative infinity to positive infinity, or we can make some transformation of y to make the y ranges from negative infinity to positive infinity. So usually if we don't have many values near 0, we have no problem to use this y as is. And x1 square footage, x2 the age, that's fine. And the problem is x3. How to deal with this x3. X3 has 3 categories: ranch, colonial, and bungalow. And how to put this in a linear model, the framework. Then this is the way. So we prepare one baseline, suppose the ranch is the baseline, then that we prepare the indicator variable for other categories. So bungalow is 1 here, and colonial is 1 here. Then if we use the square footage and the age and the bungalow and the colonial, then that we can fit y on x1, x2, and I would say x31 and x32. Okay, so we don't use this. Then we can fit the model. If we introduce indicator variable for ranch, this is redundant because the sum of these variables equal to 1 always. So that means this is the same as the intercept. So usually linear model has intercept. So we have the one redundant variable. So we have to exclude 1. So these variables, the bungalow and the colonial, so these variables are called dummy variables. And also the people in computer science say the hot encoding. Yeah. And probably you have studied in this in 5030, is that right? The students who took the 5030 from Shaoli Kon. Yeah, probably she covered it. Yeah. So the X is categorical. You don't have to worry. So just you can make dummy variables to include it. So the key is the response part. Response is continuous or binary or categorical. Yep. So do you have any questions? Okay, so yeah, this is, I think, the important technique for maybe some data analysis project, possibly your final project. And okay, so next one, the assessing model accuracy. So we have introduced the training MSE already. And not the MSE, sorry, just MSE. But we look into it in detail. And first, we discuss regression today. And the next time, we discuss classification. So regression, that we discuss 2 things. The one is the measuring the quality of fit, that we look into MSE a little more. And the next one is bias variance trade-off. So we further decompose the reducible error into 2 parts, the squared bias and the variance. Okay, so first, the measuring the quality of fit. So we have studied MSE, but the MSE is actually called the training MSE because we have the training data, x1, y1 to x and yn. So based on the training data that we calculate MSE. So we say this is a training MSE. And the training MSE is a good measure. But the one problem is that this is actually not the quantity we want to minimize. So usually that when we have new observations that we want to predict y, and then we want to minimize the errors for new observations, not existing observations. And particularly the problem is that oh, sorry, maybe we discuss it later, but the MSE is a good quantity, but it's not exactly the quantity we want to minimize. Because we want to minimize the error size for new observations. And the problem for the training MSE is the overfitting. Okay, so if we have training data, and if we have very complicated model, suppose we have polynomial of degree 99. So that is y is equal to the beta naught plus beta 1 times x plus beta 2 times x squared up to the beta sub 99 times x to the power 99 plus epsilon. Then if we plug in these 100 pairs of observations, then we can determine beta naught, beta 1 up to beta 99 so that all errors are equal to 0. Because we have 100 observations and we have 100 parameters. So we can solve the linear system, at least if all x's are different, x1 to x100s are different, then we can solve that equation to make epsilon is equal to 0. But that is a problem because probably the reality is not this complicated. For example, suppose the y is the maybe the weight and x is the height of people, then it's not realistic that the 99-degree polynomial explains the weight of the people. The degree 99 polynomial of height explains the weight of people perfectly. So this happens because we have too complicated model and we ad hocly determine these parameters to make error 0. Yeah, so here is the example. At first, on the left pane, these circles are observations. These circles are observations. So we have maybe 50 observations here. And the black one is the truth. So this black solid line is truth. And the yellow, the orange one, the blue one, and the green ones are all fitted curve with different degree polynomial. I think the degree 1 and the degree 4 and degree 20. And the yellow one is just the straight line, so degree 1 polynomial. And it fits somewhat well, but it misses the pattern of around here, or maybe around here, even around here. Okay. So yellow one, maybe orange one, isn't the best. Okay. So how about the green one? The green one is pretty close to the observation. So you can see that the green one, okay, so this point is close to here, and this point close to here, and this point close to here, and this point close to here, and so on. But actually, the zigzag curve is too complicated. So it depends on the context, but suppose that x and y has some smooth relationship, then green is too volatile. It's disturbed by the observations too much. And probably the blue curve is optimal one, right? But blue curve is the curve with degree 4 polynomial, I think, degree 4 polynomial. But if we measure the training error, the training error is observed as this and this and this. Actually, the green one that fits well to the data. So even if it's far away from the true trend line of the black solid line, still the training error is smallest. But it sounds that this blue curve looks the best to fit the black curve. So the training error has this problem. So I will explain this later, red line later. So now that we need the concept of the test MSE. So consider that we have the training data set and the test data set. So D1 and the D2. And we only use the D1 to fit the function f. Then we use D2 to evaluate MSE. So that is the more similar to the real data analysis example. So we train the model, then we have new set of observations. Then we evaluate the performance based on the new set of observations. So that is called test MSE. And the test MSE is a more accurate measure of the expected error. So here again, this is the same graph. And this red one is the test MSE. And this gray one is the training MSE. So training MSE cannot choose the best model because more parameters than better training MSE. But the test MSE, you can see that this is the bottom. So that means the degree 5, the 5 parameters. So that means the 4-degree polynomial is the best to fit the model, best to fit the data. So ideally, if we have test data set, then we have to use that test MSE to choose the model. Yeah, but still we have some, trade-off, right? So if we have data set and if we have to divide the existing data set into D1 and D2, we want to have larger D1 to make more accurate model. But if D1 is, too large, the D2 becomes too small. If D2, for example, have only 5 observations, test MSE isn't really reliable because it is just based on the 5 observations. So it really depends on the case. Maybe we have to use all observations as training set, or we have to divide it into maybe 1-to-1 or maybe 2-to-1 or something like that. So it's not entirely clear, but at least as a concept, the minimizing test MSE is useful, especially if we have very large data set. Do you have any questions? Okay, so I think the last one we want to discuss is the bias and the variance trade-off. So bias and variance. So we start with one example. So we want to predict height by the foot size, and we have 5 data points. The first person, the foot size is 27.2 centimeter and height is 176 centimeter. And 27.5, 180, 28 and 176, and 28.7 and 148, and 29.0, 183. And you can see that if the person has a larger foot size, then the height is relatively higher. It's not, exact relationship. For example, this to this, even larger foot size, but still the height is lower. But mostly, this has positive relationship. Okay. So in this case, suppose that we have a new person, whose foot size is 28.6 centimeter. How to estimate the height of this person? So we have 2 ways. One way is to choose this observation. So this observation only to estimate the height. So 184 is the estimated height. So this is reasonable because this person is closest to this person in terms of foot size. But this is just based on one observation. That isn't really reliable. So maybe you think about the averaging out these 5 observations. Anyway, the foot sizes are similar and the height are also similar. So if we take average 179.8. So we have 2 ways. And the first way, we fit, we match this number with this number. So we have smaller bias. So, but we only have one observation. So we have larger variance. On the other hand, the second way, the average of 5 heights, we have averaged out 5 observations. So we have the smaller variance. But, the average foot size of these 5 people is maybe around 28. So it's smaller than 28.6. So that means probably we underestimate the his height. So that means that we have a larger bias for this observation. Okay, so even the first observation, 28.6 and 28.7 are not exactly the same. So we have some bias, but the bias is smaller for A. So we have the trade-off between bias and variance. Bias is larger, then variance is smaller, and vice versa. And here is the theory behind it. So we have the y0 minus y. Okay, so originally we write the y0 minus y0 hat. Okay. Now that we write this as the f0 hat. So we decompose this into reducible error and irreducible errors. But here that we make it into 3 components. F0 epsilon and F0 hat. Okay, so y0 is equal to this quantity. So we have these 3 terms. And we put the negative of expectation of f hat and the plus expectation of f naught hat. And we have these 5 terms now. And then we decompose it into 3 parts. So this part and this part and this part. So this part square and this part square and this part square. And we have cross terms. We have this 1, 2, 3 cross terms, right? We have 3 terms. So, but the other terms disappear. Okay, so for example, epsilon cross term of, okay, so f naught minus, this is constant, right? This is constant. Constant times epsilon, but the expectation of epsilon is equal to 0. So the cross term, the product of these two becomes 0. And the product of this times this, the second term and last term is also 0, because this f hat and epsilon are from different observations. So these are independent. So we can decompose the product into expectation of epsilon and expectation of the second term. So that we can say expectation of epsilon is 0. So it disappears. And the first term and the second term, first term is constant, and the second term expectation is 0 again, right? Maybe it's, I put too much, but if we take expectation of this term, by definition, that is expectation of f naught hat minus expectation of f naught hat. So that becomes 0. So everything becomes 0. So this term is the same as the previous slide, but the first 2 components appears here and here. So first term is the difference between the truth and the expected estimate. So that is called bias, right? So our difference between estimate and the truth, that is bias. So then we have square. And the second term is the variance. So f naught hat, and this is expectation of f naught hat. So this entire quantity is the definition of variance of f naught hat. So yeah, so this variance of f naught hat is based on the finite number of observations. So this is called variance. So you can see that if the bias is smaller, then variance becomes larger, and vice versa. Okay. There's some good f hat makes the total error size small. But if you want to make bias small, it's possible if variance can be larger. Yeah, so we have to balance between the bias and the variance to make the best prediction model. And again, note that these 3 components are conceptual and not observed in the real data analysis, because the truth and also error is unknown. But decomposition is possible for simulated example because we know the truth and we generate errors. Yeah, sorry, I think I couldn't finish everything. So I stop here, and I continue to explain bias and variance next time. Do you have